Welcome to the deep dive. Today we're getting into Bayesian inference.
Yeah, it's a fascinating area.
We've got a set of key questions as our guide, and the idea is really to, unpack what Bayesian inference is all about and why it's powerful.
hmm
Ever wondered like how you really update what you think when you get new evidence in a sort of structured mathematical way?
That's pretty much the core of it, yeah.
So, okay, first things first. Bayesian versus the other kind, frequentist. What's the big split there?
Right. Well, the fundamental difference, it's really about what probability means to each approach.
Okay.
Frequentists think of probability as like a long-run frequency, how often something happens if you repeat it loads of time.
Right, like flipping a coin over and over.
Exactly. But Bayesian inference treats probability as a degree of belief. How sure are you about something right now?
Ah, okay. So less about the long run, more about my current state of knowledge.
Precisely. And that knowledge isn't static, it evolves. That's where Bayes' theorem comes in.
Okay, Bayes' theorem, the engine of this whole thing, right?
Right.
What are the components?
Yep, it's the formula for updating your beliefs. You've got three key parts. First, the prior.
Prior. So what I think before I see any new data.
Exactly. Your starting point, your initial belief, then there's the likelihood.
Likelihood. That sounds like how likely the data is.
Sort of. It's how probable the data you observed is, given a particular hypothesis or belief. How well does your idea explain what you just saw?
Okay, prior belief, how well the data fits. What's the third part?
That gives you the posterior, your updated belief. After considering the evidence, where does your belief stand now?
Prior plus likelihood equals posterior. Belief, evidence, updated belief. Got it.
In essence, yeah. Though the math combines them multiplicatively, not additively, but that's the flow.
Right, right. Now, calculating that posterior, I imagine it can get complex. I heard about conjugate priors making things easier.
Ah, yes. Good point. Calculating the posterior distribution directly can be, well, mathematically challenging sometimes. Conjugate priors are a kind of mathematical convenience, you could say. They're specific types of prior distributions that, when you combine them with certain types of likelihoods,
Uh-huh.
the resulting posterior distribution is in the same family of distributions as the prior.
Oh. So it keeps the math tidy, basically.
Exactly. It simplifies the calculation significantly. You start with a beta distribution, say, and you end up with a beta distribution. Much cleaner.
Makes sense. So this posterior, this updated belief distribution, what does it actually tell me?
It gives you the probability distribution for the parameter you're interested in after accounting for the data. So not just a single point estimate, but a whole range of plausible values and how probable each one is.
Okay, a range of possibilities. Now, about that starting point, the prior. You can have informative or non-informative ones. What's the difference there?
Yeah, that's a crucial choice. An informative prior is when you deliberately incorporate existing knowledge or previous findings into your starting belief.
Like using past polling data for an election prediction?
Perfect example. You're not starting from scratch. A non-informative prior, on the other hand, tries to let the data speak for itself as much as possible. It aims to be neutral.
But is truly neutral possible?
That's the tricky part. Defining a prior that genuinely represents ignorance without accidentally sneaking in some assumption is actually quite hard.
I see. So it's a bit of a balancing act. Now, what if the model is really complicated and even with conjugate priors, the math is just too much? I think MCMC comes in here.
Precisely. When things get complex and you can't calculate the posterior directly, we often turn to computational methods. Markov chain Monte Carlo, or MCMC.
Sounds fancy.
It is, kind of. But think of it as a smart simulation technique. It generates a large sample of values that effectively draws you a picture of the posterior distribution, even when you can't write down the exact equation for it.
So it's like exploring the landscape of possibilities to approximate the answer.
That's a great way to put it, yeah.
Okay. Another thing, credible intervals in Bayesian stats versus confidence intervals in frequentist stats, they sound similar.
They do, but the interpretation is fundamentally different. And this is a really key takeaway.
How so?
A Bayesian credible interval, say, a 95% credible interval, gives you the probability that the true value of the parameter lies within that range.
So there's a 95% chance the answer is in this interval. That sounds intuitive.
It is, and that's a big appeal. A frequentist confidence interval, though, is different. A 95% confidence interval means that if you repeated your entire study many, many times, 95% of the intervals you calculate would contain the true parameter value.
Ah, okay. So it's about the long-run performance of the method, not the probability for this specific interval I just calculated.
Exactly. Subtle, but a really important distinction in how you interpret the results.
Definitely. You mentioned earlier that choosing priors can be tricky. What are the main challenges?
Well, the subjectivity is one, especially with informative priors. Whose prior knowledge do you use? How strong should it be? A badly chosen informative prior can really bias your results.
Right, and the non-informative ones have their own issues.
Yeah, like we said, defining non-informative is tough. What seems neutral in one context might imply something unintended in another. There's no single perfect non-informative prior.
So it requires careful thought. Can Bayesian methods also help compare different theories or models?
Absolutely. That's another strength. You can use things like Bayes factors to directly compare how much evidence the data provides for one model versus another.
So you can actually say model A is X times more likely than model B given this data.
Pretty much, yes. It offers a formal way to weigh the evidence for competing hypotheses.
That sounds incredibly useful. Could you give a quick real-world scenario where this approach really shines?
Medical diagnosis is a classic. A doctor has some initial ideas, priors based on symptoms. A test result comes in the data, the likelihood. Bayes' theorem helps update the probability of different diseases, the posterior.
Right, because the doctor should be using prior knowledge about disease prevalence and symptoms.
Exactly. Or think about risk assessment for, say, a dam failing. You have engineering knowledge prior, you get inspection data, likelihood, and you update the probability of failure, posterior. Quantifying uncertainty is key.
Makes total sense. Bringing prior knowledge informally is powerful. Okay, so wrapping up. The big idea is that Bayesian inference gives us a mathematical framework for updating beliefs when we get new evidence.
That's the heart of it. It's a principled way to learn and adapt your understanding.
A really neat way to think about learning. So for everyone listening, maybe consider how your own views change with new information. What are the underlying beliefs, the priors, shaping how you interpret things? Something to mull over. Thanks for breaking this down.
My pleasure. It's a deep topic, but hopefully clearer now.